for the invitation to speak here. It's actually great to do it after Sridhara. It's really interesting to talk about muon colliders, and I hope you can see my screen now, that you can see my share properly and you can hear me. Okay. So first of all, I am speaking after what I am going to show about high luminosity LHC. I think this connects a lot to all the talks of this week through the specific discussions on particular subjects like couplings or BSM or the precision we can get to with differential cross sections. The speakers have already discussed what we can get to at the high luminosity LHC a little bit. So what I am going to do is try to put it all together and give you a global view of what we can do at the high luminosity LHC without necessarily going into the details, because, well, as I say, the details you have heard them in depth already through this week. So in terms of the talk, okay, I'll discuss that. And then in reply to Sridhara, who I think left already, the high luminosity LHC is going to be fundamental, but it's not going to be all. So I will finish with a few notes on things for the future. Again, without going into detail, since there was Sridhara's talk and there are after me more talks focusing on the future colliders. So that's so that you have a general idea. And well, the beginning for me is really actually going back 10 years. And again, this has been said many times this week, but I wanted to get again the message, right? We have really come a long way in just 10 years from not knowing, not having the Higgs, not knowing its mass, from it being an incognita, from being a particle that we have measured in many ways already. We have seen all the main decay modes that you can see here. You can actually go back to the talks this week and find all the beautiful explanations for how we reconstruct the decays to bosons, the decays to fermions, how we have gone to really establish how this particle decays and also how it is produced. So in a very brief personal recap, this is not all, but maybe just summarizing a little bit. Okay, so you have heard that we have measured its mass really to the per mil percent already. We have first measurements of the width. We understand we have measurements of the CP. We have measured the main production modes with already precise measurements of the cross sections. We have seen the coupling to the main standard model particles that you can see here in this beautiful scaling plot that we typically use to show to highlight how well we understand the coupling to standard model particles. And we have also done an extensive search for BSM properties of the Higgs and for extra Higgses. And so far, we have good agreement with the standard model, though, that we can do much. No? So hearing all of this, I think the question could be, so okay, so what's next? What's left to do? The reality is that we have done all of this with only a very small fraction of the data that the LHC is going to collect. We are at the beginning of the third round of the LHC, in which we will double the current data set, so we will be able to really expand what we are looking into. All the measurements that you have heard about this week will all be improved in the next years. And what is more, there is also the high luminosity LHC era, so round 4 and round 5, in which we are going to be able to expand the data set that we have by a factor of 20. So we are really, really going to have a very large playground, if you want to really explore Higgs in detail. There is a catch to that. So we are going to have a lot of data, but that doesn't come for free. So it's high luminosity means also high PILEUP. So we are going to have 200 proton-proton interactions per crossing at that is the maximum. And that implies that our beautiful detectors that were discussed on Monday will suffer. They will be, the elements and the electronics will be exposed to high radiation. In order to prevent that being a problem, to solve that, there is an extensive upgrade program by Atlas and CMS, which has the goal of maintaining at least the current performance, and in cases improving the performance despite the hard conditions. How are we going to do that? And I am not going to go in detail about the upgrades. Okay, so I am just going to focus on Higgs physics and not give you the detailed run of the future upgrades. But okay, very short to at least get the general idea. So we will have effective PILEUP mitigation. We will have better capabilities with new algorithms. We will have increased detector acceptance. So the tracker will have more acceptance, and also we will have new muon chambers, the GEMS. That's in CMS. Atlas has a similar program. Then we will have increased spatial granularity to resolve signals from individual particles, and we will have improved timing measurements with a new time detector to have a additional dimension for discrimination. So we will have difficult conditions, but we are doing a lot of work now to ensure that in the future we will really be able to exploit all this huge data set that we will get and use it, between other things, to do Higgs physics. So what do we want to do with this data? So we want to, putting it in a few questions. We want to really understand how the Higgs boson is produced and how it decays. We want to really understand the nature of the Higgs. So we want to measure its properties better than we do now. We want to understand how it couples to standard model particles. And for example, if it couples to the second generation, or also very importantly, if it couples to itself. We also want to keep on probing the BSM land, so we want to see if it decays unusually in a way that the standard model forbids, either directly to BSM particles or in ways that are not allowed in the standard model. We also want to see if the Higgs is alone. And then there is also a very important question. So we keep on talking about the Higgs as the first scalar, the only scalar particle we have observed. We want to see if it is really an elementary particle or if there is a composite nature to the Higgs. And there is a last one that I am not really going to discuss, but that I want to pass to you because it is it's the one that is underneath all of this. So we are exploring the Higgs mechanism, but we need to understand where it comes from, and this is more a theoretical question over that connects to all. And that we hope we can give input to the theories through our very detailed measurements of the Higgs. So for all of this, the run-3 of the LHC and the high luminosity LHC are really going to be fundamental. Coming back to the question at some point in the beginning of his talk, Sridhara has asked if I am going to say that the high luminosity LHC is going to be all that we need. No, it is not. But the data set that we are going to get is going to be fundamental to setting the basis and to really have a full picture of what is the Higgs that can then be expanded and really improved and brought to the next level by the future colliders like the muon collider that he has discussed. So the run-3 and the high luminosity LHC will set the basis for the future. Okay, so after this little introduction, so let's go a little now more in detail about measurements in the future. But for that, all the talk is basically structured, showing you where we are and then where we will go topic by topic. So if we start with cross-sections, the first thing to show you is where we are now on cross-sections. So I told you before, we have now, and you have seen this plot, I think, already this week, or if not, the CMS equivalent. We have now measured the Higgs production in the main production mode, so gluon-gluon fusion, BBF, associated production with vector bosons, so BH and ZH, and also TTH production. And we have done this with precisions that are already at the 10–20% level, and in the case of gluon-gluon fusion, even a little bit better, like 7%. So now the question is, we have this, how is this going to evolve in the future? How are we going to know the cross-sections and the branching ratios by the end of the LHC program? To answer that question, we do projections. So what does it mean to do a projection? It doesn't just mean to take a measurement. So for example, the Higgs gamma result with 36 inversion of arm, so the one that we had in 2016, and say, okay, so I understand this very well. Let's repeat the exercise, just looking at the expected results, but do it with 3000 inversion of arm instead of 35. this is not all that there is to it, right? I mean, it is not just a matter of taking the statistic uncertainty and reducing it. That is important, but it is not all. We need to understand how the uncertainties are going to behave in the future, whether they will improve. For example, we will have large data sets for studies for ancillary measurements. We will be able to really understand some aspects of the production of the behavior of the objects in the detector much better. We will also understand better the backgrounds, because we will have very large control samples to do background studies. And we are also going to have better detectors. So in principle, we can expect uncertainties to improve. At the same time, we are going to have a lot of PILEUP. So we can also expect uncertainties to degrade. So we have to go one by one and understand if how to project them, how to know what the uncertainty will be at the end of the LHC era, so once we get to that very large data set. Then there is something else that it's very difficult to project, which is the incorporation of new techniques. And this, we can be optimistic, but I think we are never going to be able to really capture in a projection how well we'll be able to do once one of you, especially the younger people, has a bright idea in 10 years that will incorporate and maybe revolutionizes how we do a measurement. So that is always, new techniques are always a wildcard, a positive wildcard that we cannot really properly incorporate in a projection. Well, there is again the upgraded detectors. They might significantly change the results, not only in reducing the uncertainties, but in allowing us to do things that we are not able to do right now. So, for example, we are going to upgrade the trigger system. So we may be able to open new channels that we cannot use right now, and that is automatically a gain. So we have to try, when we do a projection, you have to try to think of these things, to try to think if we are going to have, for example, a new trigger that we can incorporate. And finally, technically, so we can do extrapolations by just taking the result as we have it, okay, and projecting it, or by doing a full analysis with either a full simulation, with the same kind of simulation, but using the phase 2 detector, or with DELFTES, which is a simplified simulation approach that is simpler. The last point, of course, is that from 13 TeV to 14 TeV, there is an increase in cross-section, which is like 12% for bloom fusion. So if you want to have the numbers, and this also has to be taken into account. Now we are going to have more signal events. We are also going to have more background events, and the ratios depend on the process. Okay, so once we take all of this into account is when we can go from one measurement that we have right now to the measurement in the future and really project how it will behave at the end of run 3 or at the end of the high luminosity data set. And typically, of course, as you see here, what you see is that the results get better with luminosity. Okay, sorry for this small digression, but I thought it was useful just to remind you that it is not just a fact of adding statistics. Then, corollary to this, the other side of doing a projection is understanding how are we going to be able to model the signal and the backgrounds, and how well are we going to understand the theoretical uncertainties on signal and backgrounds, which are already today, they are very important in measurements. You have also seen this through the talks in this week. But in the future, as we have more statistics, as we understand better the experimental uncertainties, theoretical uncertainties are going to become dominant in many measurements. It is also a very complicated, there is a circular play here, because our data is going to feed into these uncertainties, for example, PDFs, or for example, modeling. There is a circle of improvement of theory and experiment here going on, that and with all of this, I think we can, and taking it also into account that there are many years for the theories to do improvements on the uncertainties we have right now, we can assume that our knowledge of the theoretical uncertainties is going to improve substantially in the next 20 years. For the projections, what we typically do is assume that they are going to improve, and we applied for most of the results that I'm going to show. What is applied is a factor of 2 of reduction with respect to what we have now. That factor of 2, in some cases, a little bit is a lot. For example, when you think of bloom production that is already done at N3LO, so it's already very precise. The factor of 2 is a lot. In some other cases, for example, a high PT or for TTH, maybe those factors are, or for the TT, for the backgrounds that correspond to TTH, that factor is maybe not that large, and it could even be that the end result is better. So we have to think that they are very important, theoretical uncertainties, they are very important in the future. They are going to improve. We have to take assumptions on how they are going to improve and then see. One of the final notes before I actually move to the results, and really I apologize for the digression, but where you get a little bit of an idea of how to do these things. I've told you before that innovation cannot be properly captured in a projection, and that is very true. Here, what I am showing here is the evolution of TTH analysis. I've picked Atlas just as a choice. The same happened in CMS, of course. Analysis evolve. What does that mean? That if you see, for example, TTH, and this is using the Higgs gamma channel, how we were doing the analysis in 70 fitting, as you see, in how they were doing the analysis fitting in that HT distribution, was already substantially different from how it was done in HTV, that already had a neural network. Very different to how it was done with the first data of 13TV, okay, with avidity, and also different from what we do now. So you see the evolution is not only the improvement in the statistics, okay, that you can see in the plots. You see that in the beginning there were just 3 events, and while now, if you look at the last plot here, you see that we have we do see the signal. It's not only an improvement in statistics, it's really that through the years we do better, and once we have more data, we can actually get motivated to find new solutions to do full analysis. So TTH has gone from being a channel that at the beginning it was not really thought that LHC could measure well because it's very complicated in topology, to the point that now we are not only measuring the cross-section, but we are even doing complicated analysis with it, like for example exploring the CP of the Higgs. So this is, I just want to motivate you on how this goes. And this effect of the projection of the evolution of the analysis also affects, of course, to the projections. The projections, how well we think we are going to do in high luminosity, depends on how well we are doing now. So typically projections, the results outperform the projections at the actual results go faster than what we project in many cases. This happened from the old SNOMAS, the old SNOMAS process to the current SNOMAS process that Sridhara was talking about. There is quite a lot of improvement in the projections on how well we are going to do in the future, as you can see, for example, in this snapshot that is the kappa T precision. Okay, reds and pinks are CMS and blues are Atlas. Okay. So with this very long digression, now I get back to high luminosity LHC. Okay, so if you remember, I had started by saying that we are now measuring, for example, blue production. The combination by Atlas says that we have a 7% uncertainty. Now, in the future, at the end of the high luminosity LHC, what we projected in 2008 is that combining Atlas and CMS, we are going to get a precision of 1.6%. This is clearly much smaller, and it's really a very precise measurement of the Higgs production. There is something, okay, of the Higgs production. This also happens to the other production modes that you see here, and in fact, we are expected to be able to measure production cross-sections at the order of a few percent. For the main production modes, and also if you look at the branching ratios for the branching ratios that are systematically limited. So you see at the bottom, I'll talk a little bit more about them after, that mu, and gamma and Z gamma are statistically limited and will still depend on the data we collect at the end of the high luminosity. The other thing that I want you to notice is that, as I promised before, the uncertainties here are split by statistical, experimental, and theoretical. Okay, so notice the importance of the theoretical uncertainties in many of these measurements. So, for example, so if you pick any of the lines, you are going to see that the theoretical uncertainties are really very important at the end of the LHC, even taking into account that these are the improved projections that are a factor of 1/2 with respect to what we have now. Okay, this is great. So the fact that we will be able to measure production cross-section and branching ratios at the few percent level is something that, in principle, it was not expected that we would be able to do. However, just giving numbers is only part of the story. Is not all. Okay, so this is something that Mauro discussed to you quite in detail yesterday. Overall agreement in rate is really only the beginning. So if there is BSN physics, it doesn't only necessarily change the global number, but it can change the shape of the distributions, how the kinematic distributions of the Higgs change. In order to be able to see this, what we have to do is look at the differential distributions. For example, this one that shows you the PT, the differential PT of the Higgs, it shows it as a function of the differential PT of the Higgs, comparing set gamma gamma and the combination. What you see here is that here the uncertainties are much larger than the ones that we were discussing before. So you see that there is a large statistical component right now that you see in the lines. So we need more data to be able to really understand this distribution properly and to really be able to model the Higgs properly and understand the production. And not only as a function of Higgs PT, but also as a function of many other variables. So for example, it is interesting to go very high in PT. The high PT area is very interesting to probe for BSM. We also want to see the angles, for example, in the distribution you have in the middle, and we also want to see it as a function of number of jets or the rest of the information in the event. With the data we have collected right now, we are now really exploring Higgs production in depth already, and we are already getting many of these results in many channels, like for example tau tau that was not necessarily it's one that is new, that we can even do differential distributions with it. But this is still the uncertainties are large. In order to really be able to rule out BSM behavior in the kinematics of the Higgs, we need much more data. And for this, RAM3 and the high luminosity are going to be game changers. So we are going to need all the statistics that the future provides to really be able to really understand properly these distributions. Coming back to the Higgs PT1, okay, so this is combining gamma gamma set and BB to be able to go to high PT, or also looking at the differential, the angular distributions. Okay, here you see for again the PT of the jet in the bottom and the rapidity of the Higgs on the top. Putting together all of this is how we can get a picture of really how we will be able to measure the Higgs in the future. And note that in the future the precisions are going to be really good. So even of some things of the order of 10-20% for high PTs. So it's where it will be still dominated by statistics. So we need all the data to really be able to paint the proper picture of the Higgs production. Another way of looking at this is not only looking at differential distributions, but also something that was discussed by several of the speakers this week, is doing simplified template cross-sections, which means picking specific bins of phase space, which have been that are particularly interesting for theory reasons, to also having been coordinated between CMS and Atlas and our theory colleagues to really measure precisely the cross-section in those bins and provide like this global view in all the decay, in all the production modes and all the decay channels that can be combined and that can be coordinated to really understand, map precisely Higgs production in all these particular bins of phase space that are interesting for doing future studies. With this, if we look at individual channels, so Atlas has prepared a new projection of these simplified template cross-sections for this SNOMAS exercise. And if you look at the numbers, you see that at high PT, using, for example, BB-bar, we can get to precisions of 10% in high PT bins. And also looking at Higgs to tau tau, you see that going at high MJA area in BBF, we can get to better than 10%. So it is really important to really see the map of the Higgs in detail, looking at this, and the fact that we can get to 10% or better in many areas already looking at individual channels is huge. One last point, talking about indirect constraints. Mauro talked about this yesterday. So all this idea of measuring kinematic distribution that I am telling you, is part of it is as Mauro told yesterday, we can use these shapes to obtain constraints on new physics from the precise measurements. So for example, we can use the Higgs PT distribution to put constraints not only on the coupling of the Higgs to the B quark versus the C quark. Okay, this is the plot that you see in the bottom, and we can also use it to put constraints on BSM, for example, the effective coupling to the blue one versus the coupling to the top. So we can really, this is just an example, and it's all, we can really do a lot of things once we look at the differential distributions. Okay, so Hope I convince you of that. I am going to move to the next topic, which is how to measure Higgs properties. Okay, so how to explore the nature of the Higgs. Simplifying it, how well can we know its mass, its width, or its spin? The mass that was free in the standard model was shown, I think, on Tuesday, that it's now known to the per mil level using SNAPSHOTS and gamma. Okay, and the measurement, the best measurement right now is the one of CMS, which is 0.11%. And this is still with only partial part of the data of run 2. The width is really very small in the standard model. We cannot measure it directly just from the shape like we can do for the mass. We have to use the off-shell versus on-shell production to really have a handle on it. But we have already a first measurement with the data of run 2 that is in agreement with the standard model prediction. And finally, for the spin, the early data in run 1 already confirmed that the spin of this new particle was in agreement with the standard model prediction, but there is still, while we have excluded purely CPO'd Higgs, there is still a possibility for mixing, and there are quite a lot of studies going on right now that explore whether the Higgs sector has a new source of charge parity violation. Evidently, all these measurements will be improved in the future. We will have more data, we can do better here. First example is the mass. Okay, it relies, as I said before, to measure it, we rely on the cleanest events, so the ones in which you can really reconstruct the Higgs. So for lepton and gamma, they have narrow mass peaks and very good mass resolution. The precision is in fact linked to how well we can measure photons and leptons, energy scale and resolution. And here's where, for example, understanding well the upgrades plays an important role, right? How well we will be able to measure photons and leptons in the future. How will, for example, the tracker upgrade impact in the for lepton resolution, etc., has a very important role. All of this goes into, okay, so how well can we measure this factor? And a recent projection by CMS shows that using the current detector, so just extrapolating, adapting the uncertainties, but still using the current detector, projecting the current analysis, we could get to 30 MeV only with set and just one experiment. If to that 30 we add the fact that we combine with the gamma measurement, that is here you see that it's like 70 in the future, we also add Atlas, and we eventually fold in the detector upgrades and the predictor tracker, we can do better than this, and the goal would be, for example, to get to something like of the order of 10 and 20 MeV. And I think this year is particularly easy to motivate to you why it is important to do this. I think we all have very in mind the recent measurement of the mass of the W and how impactful the precision measurement of a variable like this, like the mass of the Higgs, is in the standard model. So we have to measure the Higgs better in the future. Regarding width, while the mass is already a very precise measurement now, and it's going to be an even more precise measurement in the future, for the width, this is a very small parameter in the standard model, and as I said before, we cannot really probe it directly with looking at the shapes. So projecting the measurement, the result that we have right now, the technique that we use right now to extract the width from the off-shell versus on-shell ratio of Higgs production, we can get to a precision of the order of 25% with just one experiment, and 20% if we combine Atlas and CMS. So this is, again, very big. Okay, it's not trivial to measure the width of the Higgs with a collider with experiments as CMS and Atlas, and it's even if it's model dependent, if you want, it has a lot of assumptions. It's a very important measurement for the future. Connecting a little bit to the future, to the other talks of today, I wanted to pay attention, okay, because this is a completely different picture in lepton colliders that can actually really get to a very precise measurement of the width. So keep this in mind when it is discussed in the next talks. Okay, that the way we can access the total width of the Higgs in CMS and Atlas is completely different to the one that electron-positron machine will be able to in the future. And finally, CP. So here the question is whether the Higgs, even if so far we have seen it to be compatible with the scalar. We are trying to see if there is a new source of charge parity violation in the Higgs sector. For this, there are many constraints going on right now using the case to vector bosons, the production in TPH, and also both in production in decay in tau-tau. And just to give you an idea, I've picked just one of the examples, okay, which is using tau-tau decays, which you can scan the mixing angle that corresponds to either pure scalar or pure pseudo-scalar and then a mixing. Okay? So the measurements that we have right now are compatible with 0, with the standard model, but with a 20 and have a 20 degrees uncertainty. Projecting these measurements to the future, we can get to a 5 degrees uncertainty. This is just one example of how we can do this in the future. All of these results should be, so we have few projections actually, but exploring how well we are going to be able to understand CP in the future is something where we have to work more in the future to increase the number of projections that are available, and of course increase the measurements once we have the data at hand. Okay, that was for how we can understand the Higgs. Now moving to a different topic, which is rare processes. Rare here means not produced in a very abundant way. So of course, if you are talking about processes that are produced with small branching ratios or small cross sections, it is of course very important to see how will the huge statistics data sets of the high luminosity LHC will impact. There are two. The benchmark example here is mu. Mu, as you saw as Jan told you, has been one of the highlights of the run 2 of the LHC, is the fact that we have evidence for the coupling of the Higgs to the second generation. So this is trying to reply to the question of whether all standard model families get the mass from the same Higgs field. And so far, the data tell us that yes, there is the Higgs couples to the muons. Seems to couple to the muons as the standard model predicts, but in order to get observation, we need more data. So we are going to these results, just to see it in the CMS numbers, are statistically illuminated. Okay, so of course it is really important to add the future data sets of the LHC to the game to understand how they are going to improve. And in fact, if you put together the analysis, we will get to observation by the end of run 3. Furthermore, the upgrades here are very important. So if you take, for example, the CMS example, the tracker upgrade brings a resolution improvement, which is going to be really fundamental in how the measurement is done in the future. Okay, and so what you see here, for example, the other plot that I show is the projection that has been done for SNOMAS, which surpasses the projection that was done for ECFA. Okay, and this also gives you an idea of how, as I said in the beginning, projections improve in the future, right? So you see the evolution with luminosity for the measurement of kappa mu, and you see how, if you compare, for example, the diamond, which is what we had in what we did for ECFA, for the European strategy, and what is being done right now for SNOMAS, you see that there is quite a lot of improvement, at 30% with respect to the old projection. The other big question is if we can see the Higgs coupling to the charm as the LHC. And so we want to understand coupling to the second generation. There is the muon fine, but what about the coupling to second generation quarks? And this is also very, very interesting because the charm quark is the only quark for which we could measure the branching ratio. Okay, so this tries to answer the question of whether up-type quarks get the masses from the same Higgs fields as down-type quarks and charged leptons. These are difficult measurements. And it's not only a matter of statistics, we need to be able to identify charge jets. And the recent result by CMS, it has been a revolution, if you want, that has completely outperformed all that was thought that the LHC could do. Still, right now we are 8 times, 14 times if you look at the expected about the standard model, or 31 times about the expected if you look at Atlas. So we need more statistics again here. Okay, so one thing that has been done for SNOMAS is project this new result to understand how well are we going to measure charm in the future. And this new CMS result really is in another league compared to the older projection that we had. Okay, so you see here the two plots that I show are the mu. Okay, so the measurement of the mu. This is a fitting BB bar versus CC bar, and also the measurement of the coupling of the Higgs to the Charma and to the bottom at the high luminosity LHC. So here the goal is to try to see if we can actually get to seeing, so getting a precision of kappa Charma at the order of 1 or 100% at the high luminosity LHC, for which we may have to combine all the data of Atlas CMS, and in this game LHCb also plays a role. But considering the CMS result and considering, as I told you before, innovation plays a big role in analysis like this, innovation in machine learning, in tagging, in how we do the analysis, I think we can be optimistic to get it to actually see the Higgs coupling to the Charma at the end of the high luminosity LHC. Though, coming back to the comments by Sridhara before, to measure it precisely, to measure it as precisely as we do the other Higgs couplings, we need a future machine. Okay, and almost done with this section. Other rare decays, of course, again, we have a very large data set, so we can measure, we can look for rarer and rarer decays of the Higgs, and in particular, for example, to probe the lighter Yukawa couplings, okay, not only the Charma. For some of them, without going into detail of with all of them, for set gamma, we expect, we are basically there with the evidence, so we expect to measure it precisely in the future. Other examples that are more rare, so Psi gamma or Phi gamma, Rho gamma, that probe the C coupling or light Yukawa couplings, we will have more statistics to work with it. We also will have the case to quarkonia, that have a new projection known for SNOMAS, and with all of them, we can actually study the couplings of the Higgs with precision. In all, if you look at this figure here that compares the reach in terms of direct searches, this is the one. This is all. This corresponds to the older projections by Atlas. The direct searches in yellow with what we get from the kinematic feeds that I mentioned in the beginning, or what we get from just knowing the width in blue. And finally, with these exclusive searches, these channels that I am showing in this slide, you can see what is the connection between all of them for the coupling to the charm, the coupling to the strange, the coupling to the D, and the coupling to the U. Note that for some of them, especially for the light Yukawas, the ranges that we get to are really large. So the limits that we are going to be able to put in this light Yukawa, even at the end of the LHC, are rather large. And one last point, what about Higgs to EE? Well, the branching ratio is really very small in the standard model, so at LHC we can only look for deviations. The random limits are 10 to the minus 4, so 5 orders of magnitude less than the prediction in the standard model, but this is statistically limited, so of course we will do better in the future. One last point here, I said rare processes in the intro slide, because of course we are talking about rare production. That doesn't only mean a rare decay, but also a rare production mode, for example. And the big example for this is TH. That is something that we are already probing right now with staying above the standard model. With more data, we will be able to measure it properly and use it, for example, to have access to the sign of kappa T. The projections are a little bit old now, so it would be interesting to see how well the analysis for TH have improved quite a lot in the recent years. So it would be interesting to see how well can we do if we redo the projection towards the future, and of course, how well will we do really in the end once we have the data. Okay. I'm going a little bit slow, so I am going to try to. Sorry, it's a little bit early for me, so I think I'm going a little bit slower than I wanted. But let me move on. So, okay. So next question: how well putting all?
Yeah, no problem.
Okay.
So go in your own speed.
Okay, so if I put together everything that I have discussed right now, we can do a global fit of all the Higgs aspects that we know, and try to understand how well do we really know the Higgs couplings now. This was shown already this week in the kappa framework, which is a simple parameterization that is very used in the LHC experiments. They are already known to 6 to 15% with still without all the run-2 statistics and still without the eventual Atlas CMS combination that will do better than this. How well can we know this in the future? How will we know this by the end of the LHC? Okay, so from 6 to 15%, we will be able to get to 2 to 4% for all the non-statistically dominated modes. Okay, so muons and Z gamma are a different matter. So again, this is it's perhaps difficult to convey with just a chart how impressive this is, but this is really outperforms what was thought that the LHC was going to be able to do by a large factor. Okay. And again, here you can see that the impact of theoretical uncertainties is quite large. So what do we do? Apart from, as I tried to motivate earlier, we have to try to do as much as we can to do the analysis less dependent on theoretical uncertainties and improve the theoretical uncertainties. The other thing that we can do is go to ratios, right? So if uncertainties are a bottleneck, we can go for ratios of couplings, where the impact of theoretical uncertainties can be mitigated, okay? And we can have a more precise view, if you want, of the behavior of the Higgs overall. The next question that I hope that I am sure that some of you are thinking is, okay, so what does it matter to get to 2% or not? How well should we know these couplings? And the reality is that in BSM models predict deviations in the Higgs behavior, but these deviations are small in many models. So only now we are approaching sensitivity where we expect these deviations, and we need to get to this precision that I am discussing to at least better than 1% to really start to be able to prove and to really see these changes in Higgs kinematics, in Higgs couplings that we expect from BSM physics. So we need to get to the percent level and below with the high luminosity or with future machines. And one last point here is that, okay, so this talk only thinks about the Higgs and the Higgs sector, but in reality, to be able to have the full story, we need to put together all the information of the high luminosity. So we have to put together Higgs information, Draghian information, standard model information, and do a global fit. Only that is going to give us really the full picture of the high luminosity power to explore the Higgs sector. There is this plot was done by our theory colleagues, taking on the data we have provided. The collaborations are still slowly moving to being able to us doing directly these CFT approaches with all the information and with this information available. It's really complicated to do. It's a long process that will go on through run 3 and to the LHC, but it's a very interesting one that we need to put a lot of effort into in the future. Okay, those were most of the Higgs couplings, but there is one that was absent from the previous slide, which is the coupling of the Higgs to itself. This is a peculiarity of the Higgs. It gives mass to itself. That is, it has, as I think Santeri discussed yesterday, it has huge implications for the universe. Okay, on the vacuum and the Higgs field and the future of the universe. So it's really important that we probe it, that we measure this as well as we can. The way to do this at the LHC is looking for pairs of Higgs bosons. This has a very small cross-section, so it's difficult to do. And there are many possible decays. Of course, we have two Higgses. The two Higgses can decay each one to whatever it wants, and you end up having a plethora of final states. There are three that are particularly interesting, which are BB gamma gamma, BB tau tau, and 4B. What you combine, well, BB has the largest branching ratio, so it's interesting to use it. And then you combine, for example, with gamma gamma or tau tau, that are able to really reconstruct the Higgs well, to have a pair that has sufficient branching ratio and a nice reconstruction of the Higgs. Coming back to the summary of Santeri's talk yesterday, so the status right now at the end of run 2 is that, well, we have individual channels for the leading decay modes are already placed limits of the order of 5 times over the standard model, and a partial combination by Atlas puts limits of the order of 3 times over the standard model already. Adding more channels and incorporating the final 2 combination will improve these numbers, okay? And I think it is important to keep an eye on all of this through run 3 to see how well can we do by the end of run 3. I think we will be surprised with how well we do compared to now. A second aspect is that I think this was also discussed today is that, okay, so when we talk about the Higgs, typically we think about gluon-gluon fusion, so being able to see the production of two Higgses, but we can also use the other production modes, like for example VBF, to put constraints on the Higgs sector and the behavior of these beautiful particles. So for example, we can use VBF Higgs to probe the coupling of two V's and two Higgses, okay, and put constraints that are starting to arrive. These are the first results done like this and are very interesting. There are no projections of these to high LUMI, yeah? So even if it would be interesting to see how much statistic we have in the end, right now we have only the gluon-gluon fusion projections in general. Okay, so wrapping up here, how well, so if this is very important and is very little, it stands to reason that going to high luminosity, so having all the data set that the LHC is going to provide is going to be extremely important. Okay, and then for the European strategy, we did the projection to understand how well will Atlas and CMS, so all the data set of the LHC, be able to do. What we projected by then was a 4 sigma on the, so not quite 5 sigma, and a 50% uncertainty on kappa lambda, so on the measurement of the self-coupling by the end of the high luminosity LHC. Comparing the different, if you look at the plot on the left, you see the comparison of the two experiments. We both do very well, and how each one of the channels contributes to the final uncertainty on kappa lambda, and the plot on the right shows the log likelihood, okay? So in that we can exclude the second minimum, and that we have eventually a 50% precision on kappa lambda at 68%. These numbers are likely to be outperformed. Again, this is a projection of what we knew with the 2016 analysis. It is very, I think it is easy to be optimistic about the fact that the LHC will get to 5 sigma at the end of the high luminosity LHC. And in fact, what has been done for SNOWMAS is improve these projections. For example, here I show you the two plots that are here on the left are the ones that correspond to the improvement of the BP gamma analysis in CMS, and incorporating new techniques, doing the analysis better, we see how these individual projections are improved by a little bit less than 20 to a little bit less than 30%, and that is individually. So if we eventually put it all together, we also add other channels that are starting to appear, like WW gamma. We are really on track to the 5 sigma before we think. And one last point, I mean, I mentioned before there are no VBF the Higgs projection, but we have now TTH the Higgs projection. This is the third production mode, and it can give us a handle on the interplay between TTH and TTHH, and also put constraints on BSM modes and scenarios of compositeness. So it's also a very interesting avenue to follow, not only the Higgs, not only gluon-gluon fusion the Higgs. Almost done with the high luminosity LHC. This is just going to be much more exploratory, but I didn't want to finish my discussion of LHC, high luminosity LHC, without discussing a little bit about the connection of the Higgs to new physics. Okay? The Higgs is central to most of the things that we don't know about the standard model, about about the universe. It really plays a crucial role in most of the extensions of the standard model. So the fact that we have measured a boson with 125 GeV, that doesn't mean that we really know what it is, what it means, or where it comes from. One way to answer those questions is trying to see if we can use the Higgs to break the standard model. So for example, why do we need to assume that the standard model decays follow the standard model rules? Maybe it decays the standard model particles. Maybe we can see something like a decay to dark matter, or in a way that violates flavor, or that gives us rise to new pseudoscalars. Right now, the constraints we have on this kind of behavior are still rather weak. Okay, so this 19% comes from Atlas, from the coupling fit. If we project it to the future, we should be able to get to something like the level of 4% for untagged, so pure BSM or a little bit less than 2% for the invisible branching ratio. Okay, but this is from the coupling fit. So how do we do it exactly? I think this was discussed by Isabel, but the Higgs, picking one of the most important scenarios, is the one in which the Higgs can couple to dark matter. So, for example, well, there are many dark matter models. The proposal is that the Higgs couples to dark matter in a way that is called Higgs portal, and that would mean that we would be able to see the LHC through invisible decays, so through the case of the Higgs to vicinity, so things that we cannot, particles that we cannot reconstruct in the detector. Like that, we can put a handle, a limit on the coupling, and compare, for example, to other searches for dark matter in different experiments. The current sensitivity is at the 10% level, and if we project this to the high luminosity LHC, we see that we can get to something of the order of 2.5% level, so much better. Though again, this is an older projection. Okay, it's a projection that was based on trying to understand. The point here was really trying to understand how we are going to be able to deal with high PILEUP. So here, the upgraded detectors are going to be really important, okay, in really constraining and really giving us a handle to deal with the 200 PILEUP at the high luminosity. This was done with a full analysis that showed that changing the optimization, we can deal with the higher PILEUP, changing the MEF thresholds, and we can maintain the sensitivity. This Higgs invisible is perhaps the most interesting channel, but it's not only the only channel in which the only way to look for Higgs to BSM. Okay, so we can go beyond. So we can look, for example, for pseudoscalars, for LLPs, for dark photons, for ALPS, and this is a huge phase space to probe. I am not going to go in detail, all the analyses are typically limited by statistics, which means that going to the future, we are going to do much better. You see this, for example, in this 2v2 tau plot, where the purple line is the 36 femtobarns of 2016. You see how small the limit gets when you get to the high luminosity, and the red line in the bottom. Okay, and so we really need to exploit the huge dataset that we are going to have in the future. And there is a second point, which is that some of these signatures, for example, the ones that involve long-lived particles, are really going to have a lot to gain from detector upgrades, track triggers, having new handles on timing. It's really going to be an area that is going to improve really a lot with future studies. This is not all, of course. The other thing that we typically do at LHC is look, try to understand the question if the Higgs is alone. Nature doesn't seem to like that particles are alone. The fact that we have only one Higgs boson is a little bit of an oddity in the universe of particles, if you want. So we look at LHC, we look extensively for other BSM Higgses in many different topologies. The key one, if you want, is tau tau that was discussed already this week. So if we project the tau tau searches, you see to the high luminosity, we see that we will be able to probe a huge phase space much larger than the one that we are covering right now. And also you can see as well. So here you see in blue the exclusion from just tau tau, and in the line you see the exclusion coming from the fact that we have seen a Higgs boson. And can measure the couplings quite precisely. So combining all of this, combining direct searches with indirect searches, we can really exclude a huge phase space for new Higgses at the high luminosity. Tau tau is a typical example, but it's not all, right? So there are more modes that can probe different phase spaces and provide more information. One example is here is WW. There are also examples in ZZ. There are also older projections also from other models, so not just A to AH or AE, but A to ZH, for example. And there are many other standard Higgs sectors, right? There is also for example, doubly-charged Higgs channels that have different topologies and that we should explore, and that we should profit from the data set that we are going to have in the future to explore. And the last VSM slide that I have is this one, which is, okay, so I said in the beginning, so it's the Higgs. We are working on the assumption that the Higgs is a scalar. It's an elemental particle. But what if it is not? What if it is a composite state? And in order to answer this question, we cannot do it only from Higgs studies. So for example, here from the the yellow here corresponds to the couplings as measured with the 2016 data in CMS. You can compare it to the searches for a W prime, so the recast of the searches for W prime in terms of Higgs compositeness. You see that we can start to exclude quite a lot of range of composite nature of the Higgs in terms of coupling and of mass, but that we have a lot of space to prove in the future with more data. Okay, with this, now I am really almost done. I hope all this talk, I know I haven't gone into the details, but I wanted to just to give you the overall picture of how well will we know the Higgs at the end of the LHC. We'll know it really well. And these measurements that I am showing you, the fact that we will be able to measure couplings to the 50% level and di-Higgs and the self-coupling at the 50% level are really going to be fundamental in all the future studies to do beyond the LHC. But there is a beyond the LHC where all these numbers from the percent level that I am talking about will be improved, going to be able to go below the percent level to the per mil level, and to, for example, the self-coupling to the order of 20%, or if we go to very high energy or to muon colliders like Sridhara was discussing, even better. So the future is bright, and the future is being discussed right now in SNOMAS. For example, this plot from the muon collider, I think this is one of the ones that, that link is one of the ones that Sridhara was discussing. There are many other things like the coupling to strange, the coupling to electron, or the fact that from all the measurements that we are doing, we can put bounds, we can do the inverse exercise to go back from the measurements, the precision Higgs physics to the coupling's precision and understand what it means for physics. All of this is being discussed in SNOMAS, and I think it is going to be discussed this afternoon in the specific talks about the future detectors. So with this, I finish. I'm sorry that I took a little bit more time than I should, but well, just summing up, in 2012, we knew that we have a new particle. Now we have measured it quite well, and we understand the couplings to standard model particles, but we still have large uncertainties that the high luminosity LHC will be fundamental in reducing. And finally, there are still many questions that are open that we are, and LHC, the CMS and Atlas are the only experiments right now that can answer them. So we have to work hard to measure precisely this fundamental piece of the universe to really understand it well and answer some of these fundamental questions. Thank you so much.
Thank you.
Thank you, Maria. Yeah, thank you for summarizing it very nicely. I mean, it was very nice talk. Yeah, so I think the floor is open for questions. I don't see any hands. Yeah, okay, yeah, there is one from TFI. Yeah, please go ahead.
Go to slide number 18, Maria. 18 or 20? Any of them?
Which one, 18 or 20?
Yeah, this one. It's the same left plot in 20 also. Yeah. So what is this text on the right? Delta sigma for PTA is greater than 600. Is it the binning related to that? It is mentioned or what? Divided by 250 GeV most probably.
Yes. So in order to do this plot, the binning is not uniform, right? So they did the. So of course you have more data in the first bin. So the binning in the first bins is smaller. When you go to the higher bins, the binning was changed to be able to show all the spectra in the same plot, but not have huge uncertainties, right? So after 600, that bin is 250, while the first bins are, the first bin looked at is 15 GeV. Yeah? Mm-hmm. So it's if you want a way to be able to show the lower PT bins where we have a lot of more statistics, so we have more precision, and high PT bins where we are more statistically limited in the same plot.
Okay, but then I am also wondering about this lower panel. There, how come for larger PT, for PT greater than 600 GeV, the uncertainties are much less?
So, sorry, you're asking why the uncertainties are less at high?
Lower panel.
Sorry, Kajari, I didn't understand.
Lower panel. For PTA is greater than say 600 GeV.
So the band is lower, she's saying. You see the band, right? That's what you're referring to, Kajari.
Lower, yeah.
That is theoretical uncertainty.
The theoretical precision. I think part of it is just that it is I think part of it is just an artifact of the plot. Okay, so since so it is relative. So I think it's an artifact of the plot. But then part of it is that indeed at high PT, this is one of the areas in which it is going to be really important to have more developments theoretical to improve these precisions. So this is from 2018, and since then there are new recommendations for high PT modeling and uncertainties that we already take into account in our projections, but that I think this plot came before them, so it's not there. So understanding the high PT both experimentally and to be able to reduce these uncertainties, and also theoretically is really important. And indeed, this looks small. I think it is just an artifact of the plot. But uncertainties here are theoretical uncertainties here need to improve in the future, and I think since we did this plot, they have already improved.
Okay.
Let me show you. This is the comparison, right, to what we have now. Okay, so this is the Atlas that look that it goes higher. This is also VB, so it's dominated by the same, and this is an area that is in quite a lot of development. So it's an important one for Run 3 and HL-LUMI.
And later now, I don't know, maybe it is in the slide number 21, 22. So different parts of each one. This one. No, you went back too fast.
Okay.
No, this one. So there, what exactly you are trying to say that kappa C is reachable for lower values of PTH, and whereas kappa T is reachable by what exactly you mean?
Yeah, so that is, it's a little bit simplified. Okay, I think actually Mauro had I think, was it Mauro? Yeah. I don't know who had it, but somebody had the nice sketch in which you see the impact, the variation of the distribution coming from the different things. But indeed, the low PT area, which is where you have most of the statistics, that is the one basically in which we can use to see the difference in the couplings, while what happens at high PT, so BSM is easier to see at high PT, so it will deviate the tail better. So in order to do this analysis, I think the full spectrum is used there. So the circles are just used as an illustration or what is the most important part to drive these results, but in reality, the full spectrum is used.
Okay, thank you so much.
Okay, I see another question from Govinda. Please go ahead.
Yeah, sorry, it may be a very silly question. Can you go back to your slide 42?
Yep.
There you
silly questions. Don't worry.
There is a kappa lambda, k lambda. Here it is the D pairs at my 2. Sorry. No, I think there is some other. I may took some other. Where you talk about the looking for pair of Higgs bosons.
Yes.
Next page.
Okay,
yeah.
Very good. Okay.
Here you say that this theoretically deep is coming at 2, and if you move 2 more slides, just 2 more slides. Yeah, here it is the kappa lambda. This is the minimum is coming as 1. Are you talking about the same variable? If it is,
yes. Okay. So then, this is a projection, and this is the log likelihood scan. This is the log likelihood scan and the projection. The standard model value is at 1.
Okay. So
the
go
standard
back
model
now.
value is at 1.
Yeah.
Okay.
Now here, why the theory prediction? Then it is at 2. Deep.
The standard model look at where the star is at 1 as well, right? The standard model shows you the theoretical the standard model. Yes. And it's also at 1. What the red band corresponds to is what this shows is not the log likelihood scan like the other plot, but the cross section as a function of kappa lambda, and the cross section changes as a function of kappa lambda, and the minimum value of the cross section is at 2, is not at 1. So they are. I don't know if you see what I mean. So they are 2 different things.
Okay. So this is theory prediction. Even it is theory, but it's based on the data. What the observation?
No, this is the theory prediction that the cross section changes as a function of the value of kappa lambda. The prediction of the cross section is not the same for is different for depending on the value of the coupling. So it is not the same at the standard model that if you go to a BSM scenario in which kappa lambda is double what it would be in the standard model, then the cross section is smaller. there is a
No,
dependence.
so the
of
theory prediction is the it includes the BSM physics also. Is it?
Yeah, here
Okay.
all the points that are not one are BSM.
Okay.
Have a deviation with respect to the standard model.
Yeah. Okay. Thanks. I understood now. Thank you.
Okay, so I still see raised hand from TFR. Is there more question?
Yes, I'm going to.
Yeah, please go ahead.
One question that for the Higgs to mu projection. So yeah, the projection is directly from the run-to analysis just by scaling the luminosity, or dedicated PILEUP. I mean, the dedicated PILEUP sample of 200 PILEUP sample is also included here, or just it is a projection like just by scaling.
No, for here, let me see if I have another slide explaining a little bit better. I think not. Let me just a second. Maybe I have a hidden slide. Okay, well, it's not very clear, but it has a little bit more detail. Okay, no, if I do this, then you don't see it. Okay, so no, the new projection is based on the strategy used for the full run-to result. Okay. But it takes into account the increase of central mass energy, and it also takes into account the CMS detector geometry changes and the performance after the phase 2 upgrade. What that means is that they take into account, for example, the change in the resolution, okay, and they also take into account the change in the acceptance, because this is important in this case. This in the end gives you quite a lot of improvement in the result. So it is not a study done with the full phase 2 simulation, but it brings into the analysis the full run-to simulation, the full run-to, the places where the future detector will improve the current simulation. So it was taken into account. I don't know if that was clear to you. It's not simply a projection of the current analysis. That in this case, that really wouldn't be fair because of this plot that you see here that I didn't explain very well. Okay, but what this shows you is how well we will be able to see the mu peak, okay, with the phase 2 detector, which is the yellow and the narrow Gaussian, and how we see it now with the it's round 1, but okay, with the phase 1 detector. So the upgrade is going to have an impact on this, so it wouldn't be fair to not take into account to the projection.
Resolution is improving due to which aspect?
Well, it's a new tracker, right? The tracker has larger acceptance and it's also better. So we improve the resolution.
Okay. Yeah.
Okay, so I do not see any other hand. I had a question, Maria. So about the dark matter slide, you mentioned, right, how we can do the improvement there. So regarding this is, I think, VBF, if I understand.
Yes.
Yeah, VBF X invisible. So basically so this is the green line. So these are different luminosity you're showing, but do you show with respect to the current result? I missed that part. Like, how much are we improving?
Yeah, so this is not really, so here it's, well, I mean, with the current result, so there are several things there. One, the current result is the sensitivity is 10% in Higgs to invisible. I don't have the full dark matter searches. I only have in the slides
No, exactly.
the
This
Higgs
is fine,
invisible. Yeah,
right.
So the current result has a sensitivity of 10%, but this is a new analysis, right? That is the full run-to, etc. So if a project, so what was done for the European strategy is not simply project the current result, because the question when you project something that depends on MET, when you are talking about 200 PILEUP, the question there is that, okay, so can we really believe that that we are going to be able to fight against 200 PILEUP events in the future? So there what was done was not simply take the current analysis and project it, but do an analysis that was geared towards seeing if we can maintain sensitivity in a realm with a lot of PILEUP by tuning the analysis, by changing, for example, the selection criteria. In this case, what was done was, if you look at the plot in the right here, what this does is check the effect of changing the cut-on vicinity, okay, to see if we can, by changing the cut-on vicinity and re-optimizing everything, we can still maintain performance despite the lot of PILEUP. So it's not, so this one was a dedicated analysis, and the game was really show that we can control PILEUP, and we can, I think in the end we will do better than this, okay? Because this is, again, this is done like this. If you fold in all that was done to get to the 10% with run 2, I think we will eventually do better than this. Also, the VH projection by Atlas is ancient. That this is from 2013. So, and that is the number that we have right now. We don't have another set H.
Right. Still analysis are going on. So that's correct. Yeah. Okay, thank you. Thank you for answering. Yeah, so I think I do not see any other question now. So thank you, Maria.
One more question.
Yeah, go ahead, please.
Sorry, Maria, on this plot, could you explain that if we increase the minimum threshold, how come we are improving?
Yeah, well, I mean, it was an optimization study, so unfortunately I don't have all the plots here, but in the
this is what I'm wondering.
So let me see. I mean, you can, so what they did was take into account, I mean, they did the full study. Sorry, this is not a beautiful slide for showing, okay, it was just a placeholder that they had, but you can, by changing all the cuts, okay, this is just showing the minimum threshold on vicinity, but looking at all the selection, you can change the threshold on vicinity, tighten maybe other of the cuts, and really try to work with the full selection to optimize sensitivity, but prevent the PILEUP, prevent the effect of PILEUP. I can, for more details, I am sorry, but I don't have them at hand right now, but this is FTR, I think the link is in the slide, it's FTR 19017, I think.
We'll see it, yeah, okay. From CADA you can find out. Thank you, this is fine. Yeah, I don't have any other questions.
Okay, thanks, Kajri. So yeah, I think then we are at the end of the session. Thanks, Maria, and of course, thanks to Sridhar for the nice, interesting talks. And thanks to all the audience for the nice questions. So I think we are good here. So please, Kajri, go ahead.
No, I'm saying thank you for chairing the session. So bye.